a master student in Professor Ini Kim's lab at the Jocheonshik Grade School of Mobility. Today I will talk about the research I have conducted in the past. Before I begin, let me briefly introduce the background of this paper. Some of you may already be familiar with this paper. This research was initially started during the 2023 Jeju summer camp. It was carried out with the help of Ajun University students and KAIST members here. Thanks to your support, I was able to successfully complete the study and present it at the 2024 TRB conference, and even further develop it into the publication in Q1 Journal last year. I would like to take this opportunity to sincerely thank you once again for your contribution. First, I explain the background of this study in detail. In countries like South Korea, where there are many mountainous areas, tunnels are often adopted as a road structure to take advantage of economic benefit. However, due to the unique characteristic of tunnels, there are segments where drivers often face challenges, particularly when entering or exiting the tunnel. Additionally, the monotonous interior environment of tunnels can cause decline in driver attention and focus. These factors frequently contribute to accidents occurring within tunnels. Additionally, accidents inside tunnels are significantly more fatal than those on general roads, making absolutely safety measure. Many efforts have been made to improve driving safety in tunnel. Researchers have explored physical interventions such as redesigning tunnel interiors or adjusting lighting levels. However, despite these attempts, the outcomes have often fallen short, especially when considering the high economic costs. Now, a common goal among these approaches was to minimize the difficulties drivers face while driving through the tunnel. With that in mind, my study took a different direction. Rather than modifying the tunnel itself, I focused on supporting drivers directly. I choose to investigate the use of information delivery system, a more cost-effective and increasingly popular solution. The aim was to analyze how this system affects driver safety inside tunnels and whether they can offer the practical alternative to traditional infrastructure changes. To evaluate how information delivery system impacts driving safety inside tunnels, I conducted an experiment using a driving simulator. This method allowed us to recreate tunnel driving condition in a controlled and repeatable environment while also ensuring participant safety. The data collected from the simulation was then analyzed using statistical method, which enabled us to interpret and quantify the influence this system on driver behavior and overall safety. I built a realistic experimental environment using the Unity game engine and Photon server, and utilized a VR headset to simulate the lights and dark adaptation experience when drivers are driving through the tunnel. In addition, the experimental environment was set up in accordance with actual design regulation. variable message signs, and head-up display, which can reflect a real-time information transmission systems were adopted, and scenarios were set up to consider speed limit and tunnel lightning that could affect drivers when driving in tunnels. In addition, in order to clearly confirm the effectiveness of the information delivery system, we observed how drivers' behavior changed depending on their awareness of the situation inside the tunnel by recreating an accident situation inside the tunnel. All participants in this experiment were divided into groups according to speed limit and randomly assigned. In addition, the experiment was conducted with 2 participants at the time, and data was collected by conducting the total of 2 experiments with the vehicle in different positions. And data was collected on individual vehicle indicator and interaction between vehicles that participate in the experiment. After conducting normality tests on the collected data, statistical method approach for the purpose were selected based on the test result. Data collected through a driving simulator experiments were always questioned regarding their validity. Therefore, it is necessary to support the validity of the data. And one way to prove this is to conduct a post-survey. In this experiment, simulation sickness questionnaire and a presence questionnaire were also conducted, and the results are shown in the table below. The collected data can be considered reliable. These are the results of the parity test adopted to analyze the impact of the information delivery system on the driving safety of drivers in tunnel. Drivers who were aware of accident information in tunnels showed clear awareness and stable interaction with surround vehicle compared to those who were unaware of such information. And these effects also vary depending on the lighting inside the tunnels. In the case of a head-up display, the effects was clearly better than when the lighting inside the tunnel was relatively dark, confirming that the head-up display design is affected by the surrounding light intensity. In addition, it was found that the effectiveness of the information delivery system varies depending on the speed limit. When the speed limit is relatively low, some indicators show that the information was quickly recognized and the effect was more pronounced. Let me now conclude the presentation by summarizing the key finding and direction for future work. First, our study explored how communicating traffic condition inside tunnels through an information delivery system affects driver behavior. We especially look at how this impacts changes under different lighting conditions and speed limit. The results show that providing drivers with advanced information inside the tunnel improves overall driving safety. Among the system tests, the head-up display showed some limitation. Its effectiveness was noticeably reduced in dark tunnel environment. This indicates that the head-up display interface needs further refinement. Interestingly, while drivers tend to make maintain the longer headway in dark tunnel condition when using the head-up display, indicating the more cautious driving style. They also showed a greater speed variation and slower reaction times. This suggests that the head-up display may lead to more conservative spacing, but still struggle to support consistent vehicle control and quick response under low light condition. To strengthen the generalization of our finding, conducting follow-up field tests would be a variable next step. Expanding the sample size is also important consideration for enhancing statistical reliability. In addition, further study could focus on a single type of information delivery system, for example, the head-up display, and examine it more deeply from both visual and psychological perspective. By integrating these dimensions, we believe it will be possible to produce a more comprehensive insight, ultimately contributing to the advancement of driver assistance system rich in tunnel environment. Thank you for listening.
Okay, I think. Okay, so now we're ready for the questions. Are there any questions? Again, if you don't ask, you will not have lunch. You should ask. We have one question there.
Hello, my name is Lee from University, and it was a nice presentation for me because I have impressive experience about the Eternal because I saw the Korean movie named Eternal in 2016, So to me, Eternal is so dangerous, but I just wonder your research because you told us the solution about the traditional solution like the darkness or the darkness or light like this. But I just wonder if you have a thinking the solution about the fancy technology like intelligent transportation system and the autonomous and the other things. So do you have an idea of that to solve the problem in Eternal? Thank you.
Korean? 한국어로 제대로 이해를 했는지 잘 모르겠는데, 그러니까 그 ITS 시스템을 다시 한번 알려주시겠어요? 한국어.
ITS 시스템을 활용해서
네.
터널의 문제를 해결하는 생각을 했습니다.
일단은 터널은 그 위성 문제로 인해서 잘 안 잡히잖아요. 그래서 저는 뭐 ITS 시스템의 범주가 좀 넓긴 한데 이것도 어떻게 보면은 뭐 VMS나 HUD 역시 그 ITS 시스템의 영역 중 하나라고 생각을 하긴 하고 그래서 터널에 들어가기 전부터 그 터널 안에 내부의 상황을 공유함으로써의 그 일단은 그 주행 안전성이 얼마나 올라가는지를 좀 연구한 거였고 저는 뭐 거기까지였던 것 같습니다. 네.
Okay, is there a volunteer to translate that? I can. I think it's about tunnel. Any other question? I think we can still have one question.
Thank you for
for your presentation, and also today beach day. I want to study using simulation, but it's not easy, right? So, what was the most difficult thing while building this simulation in this study?
한글로 대답하겠습니다. 질문을 이해했고 이제 그 터널의 특성상 이제 입구를 들어갈 때나 출구를 나올 때 그 외부 내부의 조도 차이로 인해서 그 사람들이 이제 이제 명수능 암수능이라고 하는 거를 겪게 되는데 이제 그거를 이제 가상 환경 실험에서도 제대로 적용하는 게 가장 현실적인 문제라고 볼 수 있고, 그래서 저는 그 문제를 해결하기 위해서 이제 VR 헤드셋을 쓴 거고, 이제 VR 헤드셋을 씀으로써 그러한 현실적인 그 조도 그 반응을 이제 구현시킬 수 있어서 네, 이제 그런 문제를 해결하는 게 가장 컸었던 것 같습니다. 네.
Okay, I think that's all for Mr. Teofili. The questions are in English, so I think the international students can understand it. And I think it's okay for the presenters to explain it in Korean, because anyway, we will be in Jeju for like almost 2 weeks. So if you have other questions for Mr. Teofili, you can just approach him later on to discuss more about tunneling and information delivery systems. But for the presenters, feel free to answer in Korean, that's all.
Thank you.
Hello everyone, my name is Lina Miller. I'm from TOPS Lab in KAIST. And this study that I will be talking about introduces a multi-level clustering approach to identify and classify real-world driving data into distinct traffic conditions. We will focus on using k-means clustering to improve the precision of traffic condition recognition, ultimately enhancing traffic management and energy efficiency. These are just the contents of the presentation. So we will start with the introduction. So a little background, as population increases, roads are getting more congested, and commuting is becoming harder, and also greenhouse gas emissions are rising. In 2022, road transport was responsible for almost 30% of all greenhouse gas emissions, so making it a key contributor to climate change. As a result, multiple studies have considered traffic condition recognition as an effective method to enable traffic management and efficient use of energy in road transportation. But with EV adoption rising at an exponential rate, traffic condition recognition becomes even more effective as EVs can provide detailed and consistent driving data that helps improve real-time traffic monitoring and energy management. However, using probe vehicle data for traffic condition recognition has been challenging as probe vehicle data collects only limited information related to the driving environment. So to develop an advanced algorithm for TCR, other parameters related to the driving environment must be considered further. So as stated, previous literature using traditional TCR methods only considers vehicle parameters such as speed, acceleration, and idle time. Little attention is given to external influences which significantly affect energy consumption. So this results in broad traffic categorization like urban, suburban, or highway driving patterns, potentially reducing accuracy under diverse real-world conditions. However, vehicle behavior is strongly affected by road geometry. So in this study, we will further incorporate road gradient as a sub-feature from the traditional TCR approach. So our research objective is to develop a two-level k-means clustering method for more precise TCR and driving behavior analysis while leveraging real-world data and integrating vehicle and terrain dynamics. So we will further use torque, slope, and idle ratio to deepen the understanding of different traffic states. So the way we collected the data was through real-time driving data was collected from 54 different battery electric vehicles driving here in Jeju Island. This was collected between 2021 and 2023. The EVs had the same motor type, but differed in performance, including different power and driving ranges. Derived information included vehicle speed, motor torque, revolutions per minute, GPS coordinates, and the time interval between each record. Following this, the chip data was segmented, and GPS coordinates were matched against a digital elevation map to obtain altitude values that coordinate with each data point using the GIS software in Python. The study's approach to the two-level k-means clustering aims to provide deeper insights into vehicle driving patterns by progressively grouping data based on feature relationships. Essentially, k-means clustering works by initially locating a number of centroids on a scatter plot of data, and then the number of centroids is optimally predetermined. The next steps assigns each data point to the closest centroid based on Euclidean distance, then computes the mean of all the points for each cluster and reassigns the cluster center or centroid. This process repeats until the centroid positions have reached convergence or the maximum number of iterations have been reached. The first level of clustering identified road behavioral patterns, and the second level refined these clusters into subcategories for more detailed analysis. So in our paper, the Kalinski-Hare-Baz index was used to determine the optimal number of clusters to be used, which was 3. Level 1 clustering identified 3 distinct traffic conditions using idle percentage and average positive acceleration values, while the second level of clustering defined these groups into different driving patterns through integrating torque trajectories and road gradients. Also, we did temporal analysis of the clusters, and this highlighted distinct occurrence patterns. Particularly for cluster 3, it showed a higher frequency of data points during the morning peak hours at around 7 a.m., while clusters 1 and 2 exhibited less defined peak hour activity, but they did show peak frequency in afternoon hours around 1 to 3 p.m. Overall, the results showed that Level 1 yielded 3 main clusters. Cluster 1 was congested traffic, 2 was free flow with high speed but a weak peak. Cluster 3 was free flow, high speed, and a strong peak. High speed, and a strong peak. Level 2 refined these into 3 subclusters based on slope, whether it's up, down, or near flat, and acceleration distribution. Sometimes acceleration was aggressive. The results demonstrate the effectiveness of the approach in identifying relevant traffic condition categories, where second-level clustering was able to identify distinct patterns within each category. This underscores the importance of integrating terrain and vehicle-specific dynamics into traffic condition analyses. And the results show significant potential in enhancing the process of traffic management, vehicle energy optimization, and environmental sustainability. This provides more impactful outcomes in traffic management operations. The key benefits, as I said, are traffic management, EV energy optimization, since we can understand the traffic behavior in different conditions and the driver's behavior in different conditions, so we can optimize EV energy consumption, and this also lowers the adverse environmental impacts. But there were a few limitations to this study. Geographic limitation is one of them, which the data focused only on Jeju Island, so results may differ in regions with different road networks or climates. So for this reason, future directions and future studies could focus on collecting broader data sets and including weather conditions, city driving, and comparing city driving versus highways. We can also incorporate additional machine learning models and analyze driving behavior variables such as aggressive driving or comfort preferences. Thank you for listening.
All right, thank you very much for the presentation, Ms. Steve and you. We are now ready for some questions. Anyone? Yes.
I'm No from university, and it was a nice presentation to me because I'm also interested in clustering. So I just ask you about why you choose this K-means clustering, because there is another many clustering methodology like data-based clustering and density-based clustering and Gaussian clustering. So I just wonder why you choose this K-means clustering methodology in many methodologies.
So we did consider other hierarchical clustering methods, including HTV scan, but it's very common for this kind of cluster, which is very common, but instead of using it, we employed two-level means because other clustering techniques that we considered catches latent features for categorizing the levels, but it's not very intuitive for identifying different traffic states. So we want to clarify traffic states more clearly, so that's why we used two levels of K-means clustering for more accurate identification.
You mean the K-means clustering is have more accuracy than other methodologies?
Yes.
Okay. Thank you.
You are ready for the next question? We are actually a bit early with our time schedule, so we can entertain more questions. Yes. This is my exercise, but Hi, thank you so much for your presentation. So I'm just wondering, you just now answered about the reason that why you use the K-means clustering. Then you also mentioned about in the future work you would like to implement it after, like you say, deep learning, machine learning methodologies, and you want to expand your data set. So my question is, like as you currently mentioned about, okay, you think like K-means clustering can bring you this kind of advantage. So what you are looking for if you are going to utilize it like more like advanced in machine learning methodology? What kind of advantage that you are chasing for?
Advantage, I think the more accurately we can predict traffic conditions, the better we can control the energy management, especially for electric vehicles. And because at this point, just using EVs is not enough to reduce carbon emissions. We can also optimize the driving behavior of EVs better when we understand them better.
This for the data set or for the methodology itself, like Because like for the data set, like I think it's currently still you use k-means class when you can include those kind of features that you mentioned, right? But what if like when you are like want to use like more complex methodology, so what kind of like differences that you are changing for them? For example, like they have a better data set understanding, temporal data set understanding, spatial distribution understanding. So what kind of like advantage that you are changing for them? That's my question.
Spatial, temporal. I think the more research we do, the better we can understand with the methodology as well.
Thank you, Brian. Thank you for the question. Are there other questions? I think you also mentioned in the use of k-means clustering about the methodology being more intuitive. So like you can get more out of it in terms of meaning. Is that correct?
Yes.
Yes. Any other questions? We still have time. If there are no questions, we can do a reverse Q&A. Me will ask a question, and you will answer. But we have one more question. Thank you.
Hello, we are in Jeju. So my question is, I'm curious why collecting data from only from Jeju is a considered limitation. So in that case, what kinds of visions or terrains do you think would be better to include in future studies?
I think not better, just to capture all the differences of different cities. So maybe Seoul will have different driving features because they have different services, different roads, structures. Other countries also would be different than Jeju. So just depending on the area that we can.
Well, I just was because we are in Jeju.
Yeah.
Are there any other questions? Time check. Time now is 10:41. We still have 19 minutes. Are you ready for more questions?
So
Do you want to utilize your 19 minutes?
I think I'm okay. It's a short presentation.
Okay, I think maybe we can accommodate one more question just to end Lee's session. Okay, thank you.
I have a question about your data processing. Yeah, during your data processing, what kind of data do you like clean? So why do you clean them?
Sorry?
What kind of data do you clean? Just delete for your data processing.
For my data processing,
Yes.
what kind of data?
Yeah, do you clean?
Clean?
Do you delete?
We collected just vehicle parameter data and driving parameter data. So rough data included speed, revolutions per minute, the GPS data to get the elevation after, like from motor data, things like that.
Thank you.
Hello everyone, I'm Xiaoyu from Human Effects Lab from KAIST, and my professor is Nicole Chen. Today I'm going to introduce my work of bridging the sim-to-real gap with offline reinforcement learning, and it aims at provide a safer speed guidance for autonomous vehicle in mixed traffic. And my research scenario is a signalized intersection. So this is my content. Firstly, background and the methodology, and then the result analysis and conclusion. Firstly, I'm going to introduce the background of my research. Nowadays, we are facing problems of bottleneck in urban transportation, including the increase in urban traffic demand result in severe traffic congestion, and this kind of condition bring more pollution and consumption in the intersection. And at the same time, the safety and the security of the road users, such as the passengers and the drivers, are threatened by the mass traffic. And under this situation, more collisions can occur at the intersection. Also, the vehicles face frequent stop-and-go behaviors and unavoidable sharp acceleration or deceleration at the intersection. So we need to have smoother and safer speed profile for the vehicles. At the same time, some emerging technologies such as the V2I communication, the AI technology, and the onboard vehicle devices provide more technologies for solving these problems, including the Internet of Vehicle, the cloud computing, and the big data analytics, the real-time monitoring of vehicle operation, and the deep learning reinforcement learning, and some transformer-based models. Also, some onboard devices such as cooperative adaptive cruise control, some intelligent speed adaptation, and cooperative vehicle intersection control can provide more solutions for this kind of bottleneck problem in the urban intersection. So, how to use these emerging technologies for solving the problem? The most intuitive one is to transform the autonomous driving at the intersection to an optimal control model based problem. That's to say, you just set your goal as a optimization function to maximum or minimum it. Some example solutions can be model predictive control, the dynamic programming. The optimization goal can, if we take model predictive control as an example, the optimization goal can include the running cost and terminal cost. The ending point of the end of the point, limit of point, upper limit of point can be the earliest feasible green light passing time of the vehicle. And on the left is our research scenario. It's a signalized mixed traffic multi-lane intersection, and it includes V2I and some V2V communication. And our goal is to optimize the car following gaps by controlling the acceleration of CEV. And the HDV just follow their intuitive driving. And the second solution is rule-based math. It's also very simple and intuitive. Take green light optimal speed advisory as an example. It's a kind of system like enable vehicles to receive real-time traffic signal phase information and adjust their speed based on fixed rules. Take two rules as an example. If the vehicle is expected to reach the intersection during a red light, it initiates a deceleration maneuver to arrive just at the light turns green. If the vehicle is likely to miss the next green phase, a controlled acceleration can be applied to pass through the next green light time. And some details of it, like you can set the control range of the glossa, such as 100 meters, and deceleration is only used when the vehicle speed is above 5 meter per second, and you can set the speed factor to avoid sharp deceleration or acceleration of the system. And the third one is learning-based method, including some deep learning-based method and the reinforcement learning method. And at this page, we take reinforcement learning method as an example. Vehicle agent can learn driving strategies from the trial and error behavior between the interaction with the environment. And on the right, we show the Markov decision process. So it shows the process of interaction between vehicle agent and the connected signalless intersection environment. It includes 4 elements, including environment, state action samples, state value function, and policy. So after concluding the above 3 methods, why we choose learning-based method? The rule-based method suffer from some suboptimal performance, the limited adaptability that the static rules cannot adapt to dynamic and unpredictable changes in traffic environments, and it needs some unrealistic assumptions. It often assumes uniform acceleration or deceleration for vehicles and cannot reflect the variability of real-world driving behavior. And the optimization-based methods such as model predictive control and the dynamic programming also suffer from high computational complexity and challenges in real-time application. Because the computation time for this kind of method is very long, so it can be very hard to achieve real-time application. And also it needs big environmental implications of the road environment. And then the strength of the reinforcement learning lies in its ability to solve complex, dynamic, and nonlinear sequential decision making and motion control problems, such as this kind of autonomous driving problems, through a very human-like decision making framework. And the second part is methodology. The reinforcement learning method can be divided to three different learning paradigm, and the first one is on-policy reinforcement learning. This kind of policy is updated with the streaming data directly created by policy itself, and the second is off-policy reinforcement learning. The agent's experience appended to the data buffer, and each time you can just select some data from the buffer to update the new policy. And both on-policy reinforcement learning and off-policy reinforcement learning are online. They need to the real-time interaction with the road environment of the vehicle agent. So simply applying this kind of online reinforcement learning in imperfect simulation models can cause a very serious sim-to-real transfer gap and can bring some very dangerous behaviors. So we provide offline reinforcement learning. It's a kind of reinforcement learning that directly learn the driving policy from the fixed historical data set. It can be the data set collected by human driving or just some simulation data. And this kind of reinforcement learning can avoid the kind of dangerous interaction and bridge the sim-to-real gap. It's our goal and topic. So this page shows the dataset and the process flow. We use the CitySim dataset. It's an open source, strong-based vehicle trajectory dataset, and it we select this signalized intersection of multi-lanes. It includes 40 minutes of vehicle trajectory data and the signal timing data. Each trajectory includes the vehicle's unique ID, position, coordinations, speed, and the lane assignment. So on the right, we show the process flow of the trajectory data and the signal time and phasing data. So we need to transform the raw data into the MDP format. MDP format is basic in the reinforcement learning, as we introduced before. So it includes reward, action, and observation. This page will introduce the detailed MDP components of our methodology. So firstly is the observation space. It includes our target vehicles of the difference in position, speed, and acceleration between our target vehicle and the possible proceeding vehicle. And also our target vehicle collects the distance to the stop line, the current speed, and the remaining duration of the current phase. Because our strategy is a V2S strategy, so we need to also collect the traffic light information, as we mentioned before. Yeah. So, and also the duration of the next green phase and the current phase. The action space is the vehicle's acceleration. It needs to follow some safety and car following constraint to avoid the collision. And the reward function, as our goal is to provide efficient, safe, and comfortable driving strategy. So it includes the time to collision, the safe indicator, and the jerk is the comfort indicator. And transform the original value to a form that most suitable for calculate the reward. So this page shows the exact offline reinforcement learning algorithm that we use is critic regularized regression algorithm, and it also includes the buffer that way for us to store transitions and shows the update strategy for the policy network and the Q network updates, including the critic network and the actor network. And we use opportunity search and the grid search, combine them to define our final parameter, including the actor learning rate, critic learning rate, and batch size discount factor, which are the most important parameters in the reinforcement learning. And in the lower left of this page, it shows the training performance of the CRR algorithm. We use totally 50,000 steps and collect the change of average reward, the jerk, and the time to collision. And the result is very it's reasonable. So the last part is the result analysis and the conclusion. The first is the empirical cumulative distribution of the safety indicator, the comfort indicator, and the efficiency indicator. Safety indicator is time to collision, comfort indicator, jerk, and the efficiency indicator, time hideaway. So on the right, I show the total conclusion. Baseline method, we use the rule-based glossa as introduced before. It provides very poor performance, and the CRR is our proposed solution. It has a very good balance between the safety, the comfort, and the efficiency, and all the three indicators show the better result. We also include the behavior cloning, the online reinforcement learning TD3, and the model predictive control is optimization-based method. And the model predictive control also shows very good result, but the calculation time for the MPC is very longer than the CRR. Finally, I think CRR is better than all the other methods. And this page shows the sampled trajectories. I just select some trajectories from the different method. And on the left is the CRR, on the right is a baseline method. And each vehicle is colored according to the when the vehicle arrives at this point, what's the color of the traffic light at the time of the motion. So the trajectories are sampled every 0.5 seconds, and whether spacing implies higher speed. The baseline method shows longer interpoint distance during acceleration, indicating that aggressive acceleration and higher peak speeds. And the CRR policy produce smoother and more controlled speed profiles. So this page shows the sensitivity analysis under different ways. The weight one is the TTC and the jerk weight. And the weight two is the travel distance. We use travel distance to as the efficiency indicator in the reward function. So the worst case arises when the weight one is low and the weight two is high, result in the lowest TTC and higher jerk. So this emphasizes the need to balance the importance between weight one and the weight two. That's balance the importance between the safety and the efficiency. This page shows the discussion of market penetration rate, and the upper figure shows the performance of CV, the comparison of CV and CHV. And the lower one is the performance under different market penetration rate and the traffic volume. And this shows the increase of volume and increase of market penetration, the direction. And the time to collision increase when higher market penetration for both CAV and HDV, indicating improved safety. And the jerk decreases as ampere rises. Time headway decrease with higher ampere, reflecting that when the market penetration of CAV increases, all the performance of safety, the comfort, and the efficiency will be improved. And this page shows ablation study and the discussion. The ablation one removed the relative velocity and acceleration. It simulates the V2V communication loss, and it results higher median TTC but greater variance, indicating increased inconsistent and behavior. And the second ablation is remove the signal phase and timing information. It simulates the V2I disconnection and lead to wider TTC spread. And worse time headway, indicating the worse safety and efficiency performance. The third one is the ablation remove the jerk penalty. Remove the jerk penalty in our predefined the reward function. So it represents I connected with the reality just as represents the loss of prior acceleration data due to the delay or dropout. And the first one is I remove the low speed penalty. just simulate the imprecise real-time speed communication, and it increases time headway and reducing the efficiency and the consistency. So, going to my conclusion, my main objective is to develop a safer and smoother speed guidance policy for autonomous vehicle at urban intersection use offline reinforcement learning. And after 3 stages learning, the first stage, data preparation, second stage, training phase, and the third stage, experiment in sumo and the comparison with other methods. Our main contribution is in the proposed CRR-based offline reinforcement learning framework, balance the safety, comfort, and efficiency using real-world trajectory data. And our proposed method shows superior performance, outperform rule-based and optimization-based and online reinforcement learning-based in safety, comfort, and real-time decision. So it demonstrates that offline reinforcement learning's practical value for the safe deployment in mixed traffic without risky online interactions. So that's my presentation, and it's my email. So thank you for welcome for your question. Thank you.
Thank you very much, Ms. Xiao Yuxi. I think she's ready for some questions from the audience. Yes.
I saw your model works well with cars and intersections, but I was wondering, do you also consider pedestrians or bicycles? Like if someone suddenly crossed the street?
It's just fixed assumptions of our research scenario as only interaction with vehicles and infrastructures, including signal light. So maybe in the future research, I will consider pedestrian and the bicycles to avoid the sudden appearance of them. Thank you.
Are there other questions?
Thanks for your presentation. I have a few questions. The first is that there's a point I didn't understand. There are many indicators you calculate, like TDC, Europe. So you only calculate the indicators based on your ego vehicle, or you calculate the indicators based on the co-intersections vehicle. Like,
I think all the vehicles in our research range are collected to get an average value instead of
an average value. So, like your objective to optimize the whole system, like not only the car you control, or you control.
I control only connected and automated vehicles, and the human-driven vehicles just follow the IDM car following model in our simulation.
So how many cars can you control at the same time?
At the same time,
Yes. How many cars do you control?
I think this page shows the traffic volume of our intersection. It's just depart as maybe from 1 to 4 vehicles per second, like departure of the vehicles. So maybe the whole intersection maybe less than 100, I think.
So do you consider you use the multi-agent, like multi-agent strategy?
I think it's another problem, because if I consider multi-agent, it needs to consider the interaction and some game between the vehicles. So in this research is a single agent, but every saver is a single agent, and because it already consider the difference between the ego vehicle and the front vehicle. So I think although it's not multi-agent, so it considers some cooperation and communication with the other vehicles. So.
Also, another question is that do you consider like to extend your network? Because at present you only consider
You mean
one
single?
intersection.
Yeah. You mean the consecutive
Like,
intersection?
road network.
Yeah. I think because the CTSIM dataset only it's very limited data. So if I can find a dataset of a bigger range, maybe I will do this work. Okay. Thank you.
Thank you very much. May I know if there are other questions from the crowd? I think we can still accommodate one more question, if there's any. Maybe one simple question from me, Ms. Chayoshi. You mentioned in the conclusion part that your objective is to be able to provide a safer and smoother speed guidance for autonomous vehicles. Can you just elaborate a bit or highlight the status of current speed guidance in autonomous vehicles?
Sorry.
Like the current condition of the current speed guidance for autonomous vehicles. Like, can you highlight or elaborate more about the current problems related to speed guidance in autonomous vehicles?
I mean, connected our strategy with the device or the systems, or just current?
Actually, it's just a practical question at the latter end. I think at the end you mentioned that your main goal is to create or provide a smoother speed guidance or safer speed guidance. Can you just describe a bit more the current speed guidance of autonomous vehicles?
Current, you mean?
Like, how would you describe the current speed guidance policy for autonomous vehicles?
Current speed guidance, I think.
Compared to what you did.
I think I provide the three solutions is the current very most important strategies, including the optimal control and the rule-based control and the learning-based control. And each solution includes many different details and detailed methods. So, and at last, I compared my performance with this method. So I think it shows better performance. Thank you.
Thank you very much. Okay, let's give Ms. Shawishi a round of applause.
Good morning, everyone. My name is Sung Cho in Ajo University. Today, I'm going to talk about my research titled Monitoring and Measurement Estimation using LiDAR Sensors on Autonomous Vehicles. So first, I talk about background and purpose of the study. Traditional traffic monitoring relies on fixed infrastructure such as a loop detector and CCTV. These sensors offer limited spatial coverage and vulnerable to weather. And in response, GPS and OBD, which is sensor in vehicle-based probe vehicle data, emerged as an alternative. But however, signal loss in urban areas and inconsistent sensor quality hinder accurate trajectory reconstruction. So as a result, it remains difficult to observe traffic state and safety risk in real time. So recent research in emergency of AV-mounted LiDAR, autonomous vehicles equipped with LiDAR sensor can capture high resolution without fixed load equipment. So since AV continuously move across the network, and which may reduce deployment constraints in practice. So I am to three topics in this. So first, implement and apply a 3D multi-object tracking using MC-Track model to process LiDAR data. And second, demonstrate the AV-mounted LiDAR can be used to extract lane-level traffic indicators such as speed and density and flow and time to collision. Last, explore the potential to scale up AV-based sensing for network-wide monitoring in future traffic systems. Previous research in fixed infrastructure-based traffic monitoring, such as CCTV or loop detectors. These fixed location sensors only provide localized data at installation points, and this limiting their spatial coverage across the road network. And pro-vehicle-based sensing approaches like GPS and OVD sensor, it is the inner vehicle sensor, and so GPS data is unreliable in dense urban areas due to signal blockage, and this leading to low quality trajectories. And also OBD data varies by sensor and lacks standardization, limiting its reliability. So recently, previous studies have primarily focused on LiDAR for navigation for safety tasks, but this study focused on object detection and conflict detection. So despite these advantages in LiDAR-based monitoring, few studies transform LiDAR data into traffic flow engineering metrics. So I using the dataset in research Waymo Open Dataset. Waymo Open Dataset is the real-world driving data. This data includes driving data from freeway environment and allowing algorithm to be tested in real-world conditions. And it also large volumes of diverse data. So it contains a large amount of image and point clouds in LiDAR data. So my research process is four steps. First, data collection and pre-processing, and second, 3D object detection and tracking, and third, trajectory extraction, and last, traffic monitoring measurement. So data collection and pre-processing part is the consists of this step. So my study proposed a proof of concept framework that utilized AV-mounted LiDAR data. So I used the Waymo Open Dataset, this version, and 50 freeway scenes from the validation sense selection, and the LiDAR sensing range is limited to 150 meter, and the voxelization, it means 3D voxel in LiDAR data. So, and the bounding box filtered confidence score is this. And the trajectory filtering only object within 30 meters from the AV are retained. I used the MC track model, which is SOTA model, in the leaderboard on Waymo data. So MC track's metrics score is shown this table. So MOTA metrics, it means multiple object tracking accuracy. So vehicle in 3 meters range is higher, the high score in MOTA metrics. So I used the MC track model. After I processed my research using this model. 3D object detection and tracking follows the detection, bounding box format, and tracking vehicle trajectory steps. And the convert tracked vehicle position from LiDAR data frame is convert to global coordinate system for consistent analysis. So vehicle velocities are also rotated to global frame using the rotational part of this. And traffic metric computation is this part. So segment overview is 2 freeway segments analyzed in this study. So first is straight freeway segment and second is curved freeway segment. Each segment observed for 20 seconds per vehicle attributes position, speed, heading angle, and lane ID. So density formula is K, and distance headway, time headway, traffic flow, TTC is formula like this. So I talk about my result. So segment 1 is straight section of the freeway, and the result is segment 1 is consist 7 lanes straight freeway. So middle lanes 4 and 5 had higher densities, and the outer lane 1 or 7 showed high speed and low densities. It means this lane is free flow. So, and the last lane change is detected like vehicle ID number is 116 from lane change 5 to 4. And the traffic indicators like this. So I extract the measurement speed, density, flow center like in TTC. So temporary relief from congestion, for example, increased in speed with drop in density. And the outer lanes had stable flow, middle lanes showed transitional behavior. And my TTC analysis in tracing hold like under the 1.5. So 2 lateral risk found near upstream section, and the free flow segment prone to lateral risks. Second, segment 2 is curved section of the freeway. So lane 1 is more densely occupied than lane 2, and vehicles maintain stable and center-aligned trajectories. And the inter-vehicle gaps narrow near the downstream and indicating closer vehicle proximity. Persistent condition observed and speed remained between 2 and 5 kilometers per hour. So in this case, traffic indicators continuous low speed and high density. And sudden spikes in density and flow indicates unstable conditions. And TTC 5 layer and risk distributed across the segment. So my study in main finding and contributions in my study demonstrate that autonomous vehicle-mounted LiDAR sensor can be used to collect traffic information without relying on fixed low-size infrastructure. And my key point is enable lane level estimation of speed and density, traffic flow, and TTC. And effectively distinguishes between traffic characteristics in congestion versus free flow segments. As the adoption of autonomous vehicle increases, aggregating LiDAR data from multiple AV could enable wide area real-time traffic monitoring. So this approach holds strong potential as a future infrastructure and for intelligent transportation system. So thank you for listening.
Thank you very much, Ms. Joel Solman. The floor is now ready for some more questions. Yes.
Hi, thank you for the presentation. It was nice to hear about the many types of detecting sensors and
Yeah.
those kind of very devices that you presented. So I was wondering, you started from introducing the fixed loop detectors and fault detectors, and now the LiDAR detector, right? So not sure what you clearly did for this study. So you just analyze the data that's being collected by the LiDAR, and that's why it's called a Weibo data set, right?
Yes.
So you analyze the different kind of metric to prove that LiDAR sensing data set can be useful, right?
Yes, right.
So did you develop some kind of like many scenarios for the data or so can you clarify what you found from this study?
In this study, I'm not have scenarios in the Waymo data, but my methodology is in the freeway environment. So my scenarios like in the straight section and the curved section too only.
So that kind of data is within the Weibo data set, right?
Yes, right. 혹시 한국인이신 분?
그러니까 처음에
네네.
센싱 관련해서 그 소개를 해주셔가지고
네네.
그 3D 디텍션 같은 알고리즘을 좀 개발하신 건가?
아.
그냥 그게 아니고 일단 웨이버 데이터셋을 가져와서 그래서 지금 PDC 같은 다양한 그 시나리오에 대해서
네.
그런 지표들을 분석을 할 수 있다 정도를 좀 보여주시죠.
일단은 조금 더 영어로는 대답이 미흡했던 것 같은데 한국어로 보완을 하자면 웨이모 데이터셋을 가져온 게 맞고 알고리즘을 개발했다기보다는 리더보드에서 스코어가 높은 소타 모델을 하나 들고 와가지고 성능 테스트를 제 데이터셋에서 해본 후에 성능을 확인하고 나서 그 웨이모 데이터셋에 있는 환경 가지고 테스트를 했고 이 연구의 본질적인 컨셉 자체는 라이다 데이터를 통해서 고정형 인프라스트럭처가 아니라 그 동적인 라이다 데이터를 통해서도 교통 환경을 모니터링할 수 있다라는 데 집중되어 있습니다.
감사합니다.
Thank you. Thank you for the question. Yes. Hi. It's a nice presentation. Thank you for my presentation. And so I have one question and one suggestion here. So I would like to say, one question first, because I'm the guy who, like, as you shown there, like, traditional way to monitoring these bio feeds sensors that like CCTV installed at the intersection. So my question is, the advantage of a fixed monitoring, it can keep the fixed location for all the times, which means, for example, if I want to monitor this intersection, I can have 2 days continuous data set. But when you transfer into the AV, when you do the monitoring, it's like keep changing. So you didn't like consistently monitoring one fixed location for like a long period. So the implication is like you monitor a location with a short period. So my question is how you are going to utilize this kind of short period observation for any kind of implementation.
I think in the future, many AV vehicles consist in LiDAR. So many vehicles in the environment communicate each other vehicles, and this vehicle is
So that means like
Yeah.
each vehicle collects the data set and then they share the data set.
Oh, yes,
Or
right.
like a communication vehicle, like that type of concept.
Yes, my concept is that. Right.
And my suggestion for this research is like, I'm not so sure if I elected, but I found that there's no exact validation for the results. You shows the results, but it's not validated with the ground truth data set. You presented, you extract the PTC, you presented, you extract the traffic flow. But we don't have the real data set from Waymo, I think. So how are you going to validate this kind of work process or framework is accurate enough to follow?
My first step is detection accuracy, validate in this step, and in this result, I consist about this measurement. So as you talk about that, so I didn't validation this measurement. So I have to in future study, I have to validate this measurement, how to validate this measurement.
And the last one is, actually when we are using LiDAR, it has a limitation with like, let's say, distances, let's say, when the capacity of the road, like there are many cars at the same time, so the sensor might be blocked some way. Like, so in that way, I'm very interested about how the accuracy is going to change for individual vehicle. If the density of the road changing, if the weather of the road changing, if like as Sean mentioned, if the different kind of traffic scenarios is mentioned. So I think like the further way, if you are keep digging inside, I'm very interested about like different scenarios, especially like the sensor limitations. Because when I publish a paper, I can be judging about the original limitation of the sensor. So a comparison is needed. So that's my suggestion.
Oh, thank you.
We still have time, so I think we can accommodate more questions. Are there other questions?
Yes.
Thank you for the presentation. Because many students here last semester took a course named Navigation and Sensors. So there was an assignment that we needed to detect the vehicles through the crowd point using the LiDAR sensor. So when we did this assignment, there are many noises, and we need to use different filter and also the cluster method to get the vehicle. So I'm curious about your data set. Is that well clean, or is organized, or you need to use your own method to detect the vehicles?
This part is that.
Yes, you use the Wimo,
Yeah.
like the open source data set, right? So you can tell us the format of your data set, so what the data you have like inside. Like they are original, like cross points used, or they are like already detect the resource nearby.
Actually, this part, somebody helped to me. So, detailed answer after this presentation, I will the answer. Thank you.
Are there any other questions?